Hello kidlets, this is your second video for starlight and telescopes. I apologize, I'm a little hoarse today, I'm not feeling the greatest. So we left off looking at atmospheric windows and how that corresponds to particular wavelengths of light. And we also had talked about how each particular color you see has its own particular wavelength. And those wavelengths actually have a measurable length that we measure in either angstroms or nanometers. Well, every color we see also corresponds with a particular color. So as we increase in wavelength, as those wavelengths elongate, we have less energy and cooler temperatures. As those wavelengths get much shorter and a higher frequency, we have more energy, which would make it hotter. So we can see longer wavelength, 7,000 angstroms, 4,000 angstroms would be shorter. And the sun that we see in the yellow portion of the color spectrum has a wavelength of about 5,500 angstroms, which corresponds to the color yellow. That's why we see it yellow. Differences in wavelength and frequency also have direct consequences for studying of astronomy. Each of the different wavelengths of light, from radio all the way to X-ray and gamma ray, give us a different piece of information about space. So we can view with our eyes, we can view in optical. But some fantastic astronomy is also done in the infrared. This is where we can see star-forming regions, cooler stars. There are 90 times more cool stars and star-forming regions than actual visual stars that we see in the sky. So something has to be approximately 6,000 Kelvin for us to see it in optical, which is around the temperature of our sun. So as we get hotter, we need special instruments in order to see this, but each of these different wavelengths give us a different piece of information about space. So the study of X-rays can tell us about hot regions where atoms are ionized. This is also the way that we study things like black holes. The study of ultraviolet tells us about hot blue stars, which are capable of ionizing gas around them, and these stars are also capable of becoming supernovas that would produce black holes. Infrared tells us about star-forming regions, and radio waves can tell us about regions of cool gas that can be other areas of older radiation from space or prebiotic elements that are forming, and also galactic centers. So briefly, I want to touch on the history of the space age and how we've gotten to where we are in terms of observatories, in terms of astronomical science, and the actual history of observing. Because the sort of observing we do has been dictated by the technology that we have. And the technology that we have is largely a result of wars. So we didn't have any NASA at all. It was actually called NACA in the 50s. And in 1959, we had the formation of NASA. We had Project Gemini, which was the precursor to Apollo. In the 60s, we had the Cold War, 1961, when President Kennedy announced that we were going to go to the moon and get a man back safely. This was unbeknownst to all of the engineers in the country, who said at that point they couldn't even build a washing machine. How were we going to do that? We had the Apollo missions that ran from 1969 to 1972, which was the last person that set foot on the moon, 17 people in total, which is still 14 more people than have been to the bottom of the ocean. Then we had this period where we were no longer explorers. We had really ground-based space programs. We were no longer sending people to the moon. As we discussed in class, this was largely a consequence of having Nixon that became the president and did not see the importance of that. He wanted to spend domestically, not exploratorily. So then in the 70s, a lot of people thought that we just really backed out of space. We were no longer exploring. But the 70s brought forth this area of great observatories. We explored Venus. We sent off the Voyager missions that are now left the helio sheath and are exploring interstellar space. So we had all of these large observing programs that may not have taken people places, but it brought the science home. So all of the planetary studies were really done then. And really, until we sent New Horizons to the outer solar system, the only images we had of Pluto, of Uranus, and of Neptune that were flyby missions were done in the 80s. So we hadn't even sent something on a flyby since then. In the 80s, we built the space shuttle, which is largely seen as a flop. It was billions of dollars over budget, hundreds of times greater cost than what was anticipated. This was largely supposed to bring just satellites to space. There was this really big junction between communications and and space programs and the commercial industry of it that was just transporting stuff there. And in fact, the initial shuttle didn't even have windows for astronauts to see out of. They were largely just there to put out fires initially. There was very little science done until the 90s, at which point the shuttle was used to build Hubble. So here's some images of some of our great observatories. So what's technically considered the great observatories are these guys right here. So we have the Compton Gamma Ray Observatory, observing in gamma rays, Chandra, which is observing in X-ray, Hubble, which is observing in visible, infrared, and near UV, and Spitzer, which is observing in infrared. So here we can see those again, all of them observing different wavelengths. SOFIA is something I want to spend a minute talking about because SOFIA is this stratospheric orbiting observatory, and this is based out of Palmdale. I have also recently applied to be on this, so I'm hoping that by the time you watch this, I will know whether or not I am flying on SOFIA or not. SOFIA is really interesting in that this is a 747 that has been gutted. It has this large infrared telescope right here. When it opens, it has no effect on the cabin, on the flight trajectory, nothing at all. The pilots never know when it opens, but they do 12-hour flights. They fly at a very high altitude, so they're at the window where infrared can penetrate, so they're above ground level, and they do some pretty amazing observing, and this is far cheaper than using an actual space-based telescope, and it's still able to pick up that information because it's above the bulk of the atmosphere. So just by analyzing starlight, we're able to get information on every stellar object we're able to look at. So the energy, the temperature, the size, the chemical composition, and even their motion and rotation. So as we've already discussed, we know that color and temperature are directly correlated. And energy output plus that temperature is what yields the color that we see. So that color is dependent on temperature, and the energy output is as well. And we know that all objects radiate somewhere in the EM spectrum, and where they radiate is going to determine what color we see, whether it's in the visible or if it is beyond the visible. So we can see, just looking at this example of the constellation Orion, we can see the belt stars here, the sheath of his sword. We can see Rigel, which is a blue supergiant. We can see Betelgeuse, which is a red giant star, which is what our sun will eventually become. And both of these stars are potentially capable of producing supernovas. Betelgeuse is actually 50 light years away, so it could have already gone supernova, and we just don't know it yet. So the standard unit of measurement is the Kelvin. We know that Kelvin is about negative 273 degrees Celsius. So just looking at some common examples, human body is somewhere around 98 degrees Fahrenheit. There would be the corresponding Kelvin. Here would be our sun, 5,800 degrees Kelvin, which would be nearly 10,000 degrees Fahrenheit, and a blue star, which is significantly warmer than the sun, which would be about 62,000 degrees Fahrenheit. So the two laws that we're going to look at that govern electromagnetic radiation are Stefan-Boltzmann's law and Wien's law. So Stefan-Boltzmann's law allows us to determine how much energy something has if we know the temperature. So the relationship is that our temperature cubed is what yields us how much energy we have. So if we have 2 times the temperature, it would be 16 times greater energy, and so on. Wien's law is what allows us to determine what the temperature is if we know the wavelength. And this is the equation. It is pretty simple. We just take 3 million divided by the wavelength, and this yields what the overall temperature is. So here's an example of Wien's law, and if we look at just a general black body curve, if we see where that peak is, this is where knowing that the temperature and the wavelength is important. Wherever that peak in the black body spectra is what the temperature would be. So here, if we can see a peak around 4,000 Kelvin, we could see it would radiate in yellow. If we have a peak at 5,500 Kelvin, it would radiate this direction. So as we increase in temperature, we would be shifting then in our wavelength. So just an example for you, if we were to look at mammals that radiate at 300 degrees Kelvin, trying to look at what wavelength that would be, and if you work that out, you just have to rearrange your equation because we know the temperature and we'd be solving for wavelength. And your hint here is that this is not visible. We're looking at a particular type of mammal that does not only see in the visible portion of the spectra. Then your other example is if we take a look at a fire, which is 1500 degrees Kelvin. And if we were to figure out which wavelength that would be, that should tell you which color we would see the fire in. So blackbody radiation is a way that we can classify the peak of the maximum wavelength that any object emits. And this is going to determine how we see it, whether we detect it in a particular band of the visible spectra or if it's outside of the visible spectra. So this whole curve that represents the peak of maximum radiation or maximum wavelength is called a blackbody curve. And a perfect black body would be a perfect emitter and a perfect absorber. So it wouldn't emit anything. It would appear as black, hence black body. And all stars emit black body radiation. So they would have a peak at which they radiate, but a perfect emitter would not emit anything that we could actually see. So for our sun, the maximum wavelength occurs in about the yellow portion of the spectra, 5500 degrees Kelvin. But hotter stars are going to have that peak wavelength that is shifted, and that would correspond to a different color. So cooler stars have a lower peak wavelength. They would have that longer wavelength over here, because they would be cooler, hence longer wavelengths. So hotter stars are going to have that peak of the black body shifted towards the shorter wavelength colors or shorter wavelength portion of the spectra. So here are a couple of examples. This guy that peaks beyond the blue or beyond the violet, the ultraviolet. So this would only be visible in ultraviolet. An example of this would be the chromosphere of the sun. The chromosphere of the sun does not emit any visible light. It can only be seen during eclipses. But this would lie beyond the photosphere. This is the outer layer of atmosphere, and it peaks in UV. So you have to look at it with UV detectors to actually see it at all. So here would be a star that peaks in blue. Here would be one that peaks in the infrared. Star-forming regions, or baby stars, before they have actually completed fusion, are only visible in the infrared because they're not quite hot enough yet to have the processes that would actually get them to peak somewhere over in the visible portion. They're still pretty cool. They have to be about 4,000 degrees Kelvin to actually be visible in the visible portion of the spectra. So here we can see some examples of different colored stars and how those correspond to temperature. And we would assign these each a different spectral class. You don't really need to know this yet, but when we do learn about stars, you will know all of their spectral classes and then what their classifications are as well. So the hottest star is a type O, spectral class O, blue star, and you can see that this is very hot. It can be up to 50,000 degrees Kelvin. They've actually found the very hottest star that is 100,000 degrees Kelvin, all the way down to a red star, which would be a class M, and this is somewhere around 3,000 degrees Kelvin. Our star is a class G yellow star, which is somewhere between 5,000 and 6,000 degrees Kelvin. So that's our sun. So where it says Sol, that means sun. So here are some examples of each of these. These are all visible in the night sky. These are bright sky objects. So we can see Sirius, Procyon, Wolf Star, and Alpha Centauri b. So these are all stars that we can view in the night sky at any time, which all have different peak wavelengths, which would correspond to a different color that we would observe.